induction motor, it's already fixed. We cannot insert externally any resistance. So this slip ring induction motor, by inserting an external resistance, we can control its current. By controlling the current, current is directly proportional to the torque, so we can control the torque as well. So this is one of the advantages of the slip ring induction motor. So here we have to study for the design of the slip ring rotor. So the following factors are to be considered in the design of a wound rotor or slip ring rotor of a three-phase motor. So first thing what we have to see is the number of slots. So the winding is such that it results in integral numbers. Yesterday also I have told you, we have to make the slot such that the rotor teeth and the stator teeth should not interlock, and there is no problem of crawling. So problem of crawling will happen when your stator slots and rotor slots would be either equal or integer multiple of each other. That means an even multiple of each other. If it is odd, okay, no problem. So the winding is such that it results in integral multiple integral number of slots per pole per phase. So fractional slot winding may also be used with number of slots as multiple number of phases and pair of poles. The number of rotor slots should never be equal to the number of stator slots. See, if the number of rotor slots is equal to the number of stator slots, the induction machine will never start because of the problem of magnetic hum or cogging. This phenomena cogging. Okay, so it should never be equal. So we are always using an integral multiple, not an equal. The number of slots per pole per phase is generally taken to be greater than 2, or equal to 2 or 3 or 4. It may also be taken as 2.5 to 5 for fractional winding. So now we have to understand, see, number of rotor slots. If let SR is equal to number of rotor slots, okay, P is equal to number of poles, QR is equal to number of rotational slots per pole per phase. Your dr is equal to diameter of rotor in centimeter, and your this SR is equal to rotor slots. No, this is YSR, that is rotor slot pitch per centimeter. This is the slot pitch per centimeter. That means now if you have to calculate your stator, this your number of rotor slots, you can calculate with respect to YSR. YSR is what it is, basically the number of rotor slots we can express in terms of YSR. So we can relate it with the circumference of the rotor divided by YSR is equal to your stator slots. So this is the relationship between these. Now one more thing is there. So now we have to go for the number of turns. This thing over here, which I have written, I'll be explaining you. So number of rotor conductors, if you have to calculate, first of all, it was with respect to number of slots, that is stator slots and your rotor slots. So number of rotor conductors. So this is number of rotor conductors. Again, you have this formula: stator EMF per phase ES is equal to 4.44 F 5 max TS number of turns KWS, where KWS is what? Winding factor. That is the stator winding factor. Similarly, here in terms of rotor EMF per phase, ER would be 4.44 F5 max TR KWR, wherein this KWR would be your rotor winding factor, and your F is frequency, that is in hertz. Your phi max is your maximum flux per pole, that is in Weber. Your this TS is number of stator turns per phase. Your TR is number of rotor turn per phase. Now you can write down, you can compare this, you can divide equation, this ES equation by ER equation. So ES by ER, when you are dividing, of course your 4.44 will cancel. F will go, this F will go, phi max will go, phi max will go. You are left with TS KWS TR KWR. So here you have TS KWS TR kWr. So from here you can write TR. So suppose TR you have taken here, so you can write TR for this cross multiplication, TR here and this term here. When this term comes here, it will become ER by ES, and here you have taken TR. So here it is left as KWS. In the numerator there is TS KWS, and this term is coming here, so it is becoming ER divided by ES. So we have seen that number of conductor per phase, this is for single phase, is equal to 2 TR. If it was for three phase, it is 6 TR, isn't it? 3 into 2. So number of conductor for this 2 TR is equal to what? Z for per phase. But number of conductors for three phase would be, that Z would be equal to 3 into 2 TR, that is 6 TR. So your this is number of rotor conductors for three phase system is equal to 6 TR, same like the earlier dimension. Now the third factor in case of a slip ring induction motor would be your rotor current and your conductor area. So your rotor current you have seen is almost 0.85% of your stator current, because all the torque, all the air gap flux, that is, will not link with the rotor, so there would be some wastage. So that is around 15%, which in the previous classes also we have calculated. So let us assume that the rotor mmf is 85% of stator mmf. So now that is there. We have one more thing is that, so zr was equal to your mmf on the rotor side is, see, this is for a single phase, it would be twice ir tr, and for three phase it is into 3. So same thing, your ir tr, so here also stator it would be 0.85, 2 into 3 ISTS. So this 2 into 3 and 2 into 3 will cancel. Here also 2 into 3, 2 into 3. So here you are left with 0.85 ISTS, 0.85 ISTS. Now IR is here, TR you bring down. So you get around IR is equal to, your rotor current is equal to 0.85 times your stator current and number of turns in the stator divided by your number of turns in the rotor. Now your current density, this is of the rotor, this rho r, delta r would be equal to what? Ir by ar, ir by ar. Now if you want the area, so area would be equal to ir by delta r, and this delta r happens to be 3 to 5 ampere per meter square. Here you have to be careful whether this is millimeter or meter. Okay, so this is usually millimeter square. I think if this is given in, if this is given in meter square, no problem. If this is given in millimeter, you have to change. Okay, please switch off the mic. Now, size of the rotor tooth, slot dimensions. This is the fourth factor which you are calculating. So I can see also simultaneously whose mic is on. So please switch off. Size of rotor tooth, slot dimensions, flux density in the rotor teeth. Now you have to take into consideration the rotor teeth is somewhat like, this is your this is the teeth of the rotor. So here you have to see the maximum, this is the teeth. So here you have to see here. Yeah, any doubt you are having? So flux density in the rotor teeth is around 1.3 to 1.7 Weber per meter square, which is being calculated from the statistical data from the machines designed over the years. So minimum area of rotor teeth per pole. So minimum area of rotor teeth per pole is given by your, see, area is what? Your BTR max. BTR is what? Your B max is equal to, B max is magnetic field density. So B max is phi max by A. So your area would be equal to, phi max by B. So minimum area would be equal to, it depends upon maximum BTR. If you are increasing this your magnetic field density, naturally area of copper required would decrease, which we have also seen in our previous classes when we have studied the transformer. So this we have studied. So phi max will remain as it is. BTR we have written flux density in the rotor teeth. It happens to be between 1.3 to 1.7. So the maximum value is 1.7. So we have considered here 1.7. So this is phi max divided by 1.7. Now another thing is that, again, if we have to see the minimum area of the rotor teeth per pole. So minimum area of the rotor teeth per pole, this is the numeric value. Now if the numeric value is 5 max by 1.7, number of teeth per pole would depend upon the stator slots per pole. That is the this SR value which we have seen here. This SR, number of rotor slots. So it would depend upon number of teeth, that is the rotor slots per pole, into minimum area of one tooth. So minimum area of one tooth would be what? Area would be, tooth is rectangular in cross section. It would be the length and the breadth. So that you have to take into consideration. Minimum area of one tooth. Here he has written L1, that is the length, and this WTR minimum, that is the width. So because minimum width we are considering again, so this formula we got SR by P into L1 into WTR minimum. This is equation number 1 and equation number 2. We can compare now. These both the equations are equal, right? This is also giving you the minimum area, and this is also giving you the minimum area only. So you can equate the equations. So you get SR by P into Li into WTR minimum is equal to your 5 max by 1.7. So now you want the minimum width, WTR minimum. So this WTR minimum will remain here. Phi max by 1.7 is here. This phi r by P will go in the denominator. This Li will go in the denominator. So you arrive at this WTR minimum. It happens to be phi max divided by 1.7 into your del R by P. This is your current density del R, and this is your maximum flux, average maximum flux. Your Li is the length. So minimum width of rotor slot is given like this. And also your rotor slot per pitch, rotor slot pitch, that is your Ys is equal to WTR, that is your WTR this width plus your WSR. So let this DSR be the depth of rotor slot in centimeter, and WSR be the width of rotor slot in centimeter. One empirical formula also you have to know, like there you used to study L by Z. L by Z. Z used to be pi d by P. That is length of pole to the pole pitch. So that was L by Z. So L was the length of the pole, and this was the pole pitch. So L by Z was pi d by P. So similarly here, this length is given as diameter and width is given as WSR. So this DSR by WCR happens to be 3 to 6. Okay. Another important concept with this is depth of rotor core. Now here you see this is DCR, this is DCH, and this is DSR. So you have to study again how much depth it is having. So let DSR is equal to depth of rotor core in centimeter. DSR core, and see core, because rotor will also be having some core over which it is wound, and this is the winding over which the slot DSR is given. So this is the depth of rotor slot in centimeter, and DSH is your diameter of shaft diameter, which, see, with rotor you have one shaft also that is coming out. The main rotor is this part only, and that shaft also is coming out. So this is the diameter of the shaft, that is also in centimeter. And dr is the diameter of the total diameter. Dr means from here, this full total diameter of the rotor in centimeter. Again, you can write that flux density in the rotor core, that is would be equal to how much area on the rotor core, not flux density. Flux density, it is some mistake here. So that would be equal to 5 cr by how much? See, here also we have studied, here also this was here, yeah, this is your area. Okay, this is 5 max by BTR. Similarly here also same thing. we have phi cr by bcr. Okay, so this is my equation 2. Again I can relate this area to the area of the rotor core. Now my area of the rotor core here would be length of my rotor and my what I say, depth of the rotor core. Li into dcr would be equal to phi cr by bcr. So here you can write Li into dcr would be equal to phi cr by bcr, and this dcr happens to be phi cr bcr into Li, and this dimensions you have to take into consideration, and it should be not in meter, it's centimeter. Please correct over here, huh? Centimeter. While writing it happens sometimes, you are thinking something, you note down something, so I'll correct also while I'm uploading it again in the Google Classroom. So this is in centimeter. Again, diameter of slot is equal to diameter of rotor. So this also you have to is equal to twice into depth of the rotor slot plus depth of the rotor core, because this diameter of the rotor would be the total rotor slot plus the depth of the rotor core. So from here you can write dch is equal to dr. This is the diameter of the slot. Diameter of the slot would be equal to, how much it would be equal to, it would be equal, this is the diameter. Okay, the total diameter is this. So diameter of the rotor means only from here to here you want, so you have to minus certain things. So again you have to see diameter of the slot dsh is equal to diameter of the rotor, that is your diameter of the rotor, minus twice depth of the rotor slot, this dsr, and plus depth of the rotor core. So this formula is also very important. Hope you have understood. If you are having any doubt, please tell me at this particular point. I'll explain. So I'll move to the problem. Let's focus on the problem. The problem will do more clear understanding of the subject. So an 80 kilowatt, 440 volt, 50 hertz, three phase, 8 pole induction motor with slip rings has 65 stator slots with 5 conductors per slot. If the open circuit voltage measured across two slip rings is not to exceed 350 volts, find a suitable rotor winding. Okay, so you have to calculate the stator slots, that is SR, number of slots. Okay, then number of conductors per slot, coil span, open circuit voltage between slip rings and approximate full coil span, open circuit voltage between slip rings and approximate full load current per phase in rotor. Assume efficiency to be 0.85 and power factor to be 0.8. So obviously first we'll write what are the terms given. So the terms given is the rating is the power output power rating is 80 kilowatt. Okay, and your this slots per conductor, 5 conductors per slot. Conductors per slot, that is ZSS, is given as 5, and your frequency is 50 hertz. Your open circuit voltage of the slip rings is less than or equal to 350. Your voltage is 440 volts. Your efficiency is 0.85. Power, this is your power is this you number of poles is 8. Number of poles, how many? Yeah, 8 pole. Pole is 8. Number of poles is 8. Your power factor is 0.8. Now your stator slots, it's given 8 pole induction motor with slip rings has 65 stator slots. So stator slots is given 65. So now you have to calculate the stator slot per pole per phase. So stator slot is 65. Now per pole will come 8, per phase will come 3. So it happens to be 2.7. M happens to be 2.7. Now let's go for the how many rotor slots per pole per phase we will require. Let us suppose the rotor slots per pole, because S is given, SR is not given. So SR we have to calculate first. So let the rotor slot per pole per phase is equal to Q. So rotor slot should be a multiple of Q for integral slot winding. So we always see that we are doing an integral slot winding to avoid the cogging and the scrolling phenomena. Yesterday also I explained that. So we need an integral slot. So number of rotor poles is equal to number of stator poles, because how many number of rotor poles would be there? The same similar number of stator poles would be there. So we can have now. I told you the value of Q is either equal to 2 or greater than 2. It cannot be less than 2. So let's suppose, see, this is this is 3 and 8. Rest will change. 3 and 8 will remain same. Rest will change. Why? Because 3 is the number of phases and 8 is the number of poles. Now here Q value 2 I am putting, so 2 it is coming. Q value 3 I am putting, so 3 is coming. Q value 4 I am putting, so 4 is coming. Rest number of poles and number of phases is remaining same. So I can see my Q value is either 48, or it is 72, or it is 96. Now that means I can take my stator slots, that is my rotor slots, either 48, 72, or 96. Less than this value is discarded, more than this value is discarded, but anything between these values is okay for us. Now how do I take, which value should I take? Should I go for 48, 72, or 96? See, in this wound rotor induction motor, to eliminate harmonics, SS, that is stator slots, minus SR, that is rotor slot, should not be equal to 0 plus minus P, or plus minus 2P, or plus minus 3P, or plus minus 5P. So that means it should not be equal to, again, plus minus 1, plus minus 2, plus minus P minus 1, and plus minus P plus minus 2, and similarly plus minus P plus minus 3, like that. So for P is equal to 8, you can say SS minus SR should not be equal to 0. Should not be equal to 0, or should not be equal to plus minus 8. Now from here it is coming. See, this 0 value is this value, 0 value, and plus minus number of pole is 8. Hence this is coming 8. Plus minus 2 into 8 would give you 16. Plus minus 3 into 8 would give you 24. Similarly, plus minus 5 into 8 will give you 40. And here plus minus 1, plus minus 2. Similarly, plus minus, here you see 8 minus 1 would give you 7. 8 plus 2 will give you 10. Okay. Similarly here, plus minus P plus minus 2. 8 minus 2 will give you 6, and 8 plus 2 will give you 10. So these values you cannot take. So these are the values which you cannot take. But SS minus SR can be equal to plus minus. It can, apart from that, see, 3 you can take, 4 you can take, 5, 11, 12, 9 you can take. So let's suppose SR is equal to 50, we will suppose. So what does it mean? We are supposing, let's suppose SR is equal to 50. So SS minus SR is equal to 65 minus 50. So is equal to 15. Now if this value you are getting SR minus SS 15, or you can also take SR is equal to 48. Let's suppose this is SR is equal to 48. So you'll get 65 minus 48, you will get 17. So 17 value can you take? Yes, you can take the value of 17. Why you can take the value of 17 also? So this means your rotor slots can be 48. Okay, because you are getting these values which will eliminate the harmonics. But if you are taking any other value like this, and you are getting the difference to be 8, 16, 24, 40, or this 1, 2, 7, 10, 6, like this, if you are getting, then you cannot take these values. So hence we will take for see. And one more thing, one important thing here is, in the very beginning I have told you, usually what happens is that the stator slots and the rotor slots are very nearby, or are nearby, or in fractionally, if it is fractionally pitched, then they are integral multiples. But can your rotor slots be greater than your stator slots? See, your stator slots is 65. One thing, by getting the table, not doing all this, if you don't want to do all this, some shortcut I will tell you. This is 48, right? This is 72. How much is your stator slots? 65. So obviously it cannot be 72, it cannot be 96. Directly we can write 48. My stator this rotor slots would be 48, because it cannot be in the very beginning. I have told you here, in the beginning only we have told in the problem. See, almost your number of rotor poles and your number of stator poles and your this poles are equal, but as far as your slots are considered, they are have to be nearby value. They cannot be like more than this thing. Okay. Now let's go for the rotor induced voltage per phase. So actually that connection is what they mentioned anything regarding the connection. 440 volt 50 hertz 3 phase 8 pole with slip ring has 64 slots with if the open circuit voltage measured from, don't find a subject rotor winding. See, usually they have, as this machine is concerned, induction machine is concerned, it usually operates in star. You know why it usually operates in star, why not in delta? Tell me. See, if you will operate it in delta, your phase voltage and line voltage would be same. But if you will operate it in star, what will happen? Your line voltage decreases by root 3 times. Okay. So when your voltage decreases, what will happen? Automatically your starting torque will also lower, because torque is directly proportional to your voltage, and you can insert the resistances also. So it is better, because your starting torque is in an induction motor is 200% times the running torque. So you, it is better for a smooth operation of an induction motor to start it in to run it in this star connection. So if it is not mentioned and it is your wound rotor induction machine, you can always take it in star, and you now you can get these values. So your the rotor induced voltage per phase, this is per phase would be E2, that is 350 divided by root 3. Now you already this equation we calculated, that is this T2 here I have written, or TR is equal to E2 E1 into TS. Okay, we can write in other terms, what is T1? T1 is number of stator slots into number of conductors per slot. So number of stator slots they have given 65. Number of conductors per slot also they have given 6. And sorry, number of conductors per slot, how much they have given? 5. Yes, they have given 5. 65 into 5 divided by 6, you will get around 64. You just check. 65 into 6. Okay, I'll only check. 65. Yeah.
Sir, 65 came, sir.
6, no.
60 answer.
65 into 5. Wait. Some noise is coming. 65 into 5 divided by 6. Yeah.
64.16, sir.
Yeah, 54.16. So here it has to be 5, not 6. 5. Because number of conductors per slot is 5. See here. Something will happen. I don't know. See, number of when you are seeing the problem, there's this okay. See here, 65 stator slots and with 5 conductors per slot. So you have to take this value to be 5 over there, not 6. Okay. So when you are taking that value, you will get the value of 54.166. Now I just calculated. Okay, 54.166. So this would be 65 into 5 divided by 6. So you get this value of 54. So you get the value of T1. T1 is what? Number of stator slots given 65 into number of conductors per slot given 5, and you get this value 54. Now you want to calculate the value of TR. This is the rotor turns per phase. So again, this is E2 by E1 into T1. So E2 is what? This E2 is the open circuit voltage that is given 350 by root 3. E1 is the stator voltage. Basically this is ER and this is ES. This is the rotor open circuit voltage. ES they have given 440. Again, if you go to the problem, see here 440 they have mentioned. So this is your stator supply voltage, whatever voltage you are supplying, because induction motor already I have told you is a singly fed machine. So whenever you are giving supply, you are giving to the stator. So stator is the side which is singly fed. So this singly fed machine will be like this only. So you have this E2 is your 350 by root 3. T1 you just calculated 54. Yeah, any doubt you are having? Any point? 54. Again you have T2 is equal to E2 by E1 into T1. T1 value you know it is 54, E2 you 350 by root 3, and this is 40 440 by root 3 cancel. 350 by 440 into
43,
T1. So
43.0, sir.
43, yeah, you'll get around 43. Value is around 43, 42.9, 43. Now you know the number in rotor side. If you have to calculate the number of conductors, so it would be equal to 6 times how much in the rotor side? Rotor is your T2, 6 times T2, because this is your rotor TR, na. So this would be 6 times number of rotor conductors would be ZR would be equal to 6 times T2. So this 6 times T2 is 6 into 43. So you get around 258. And now you have to that what we write like this, gamma r, na, gamma r, that gamma r, that is conductors per slot, gamma r, that is equal to ZR by your this SR, rotor slots. So SR, you can take 48. Here you take 48 only, or you can assume 50 also. So anything, if you take it 48 or 15, no problem, you can take any value. 258 divided by 48 if you will do, so it will come around 5.375. Or if you are doing around 52 58 divided by 50, so it comes around 5.16. So whether it is 5.16 or 5.37 divided by 50, you cannot take in fraction. You cannot, conductor per slot has to be some next in. So it is better to take the next integer value, that is 6. So you can see there I had earlier, for explaining purpose I told 50 if we will take. So here we can take it as 48 all. Okay. Now coil pitch for full pitch winding. Now one more thing is that number of slots and number of poles. See, again, number of slots and number of poles. Number of poles is 8, and number of slots, if I have taken 50, so it is 50 by 8, 6.225. If I have taken number of slots as 48, it is because I can take any value between 48 and 96, but it should be less than 65. So I can take it as 50 also, no problem. But again, that SR minus SS ratio should not cause harmonics, and we have to see to that the difference between them is like 15 17, like that we have to take. So why here 50 I had considered is because 50 was giving me lesser difference, so it would have induced more flux. So we can take 48 also, 50 also, any which way, but we have to see that this thing, it should see, it should eliminate the harmonics. So we cannot take these values. Okay, the difference between them should not be this 0 8 16 24 14 1 2 7 10 6. But it can be, the difference between them can be 3 4 5 11 12 13 9 15 17, like that. 17, but these values if they are coming, see, 17 can be, but if the difference is coming 16, you cannot take. Now 24 you can not take, 23 you can take, 22 you can take. These values are, apart from these values, whatever is the minimum difference you can take. So once I taken 50, so I 65 minus 50 is 15. Now if I will take the value like 60 here, 60, so this difference would be 5 only. But one thing is there, we have to consider also these values. This is 48, so next to this 48 only we have to see, or if this is 72, next to it only we have to see. So better is like we can design any which way. Design is like independent. A person can design, like two persons can design differently, but they should follow the criteria. These criteria they should follow. Any person can take 60 also, some other values also. Accordingly this numerical value will change, this value will change. So I will evaluate like that only. Here I considered like 50, somebody can take any other value also for this purpose. But the main function is that It should not fall. SS minus SR ratio should not fall. If here the difference is coming 8 or 16 and you have taken that type of design, means design is wrong. If if the difference is like this and you have considered for minimum value, so somebody can write 60 also. So 60 when I am writing, so I am getting 5. 61 if you write 65 minus 64, okay, no problem there. But usually odd numbers we avoid. Even only we need now 65, 62, so 3, that also you can write. So the maximum value you can write for this is around 62. Okay, like that you have to do. So you have to keep this difference into mind. Here I have taken for the lower value. So yeah, any doubts you are having, you tell me. See, I am again telling you this design is independent there, so you must not matlab, fix upon one particular value. Like okay, sir has taken 50, so we'll also take, or 48, we'll also take, like that. I am telling you how it has to be taken. How you can design. There are some constraints on the design. The harmonics should not let it to crawl or cog. That's why we are designing it in such a manner. So one more thing now you have seen is that to have a coil span pitch as 6. Now if we want a coil pitch as 6 here, we have SR is equal to 48 and SS minus SR is 17 within limit. Within limit means we can take this. So this thing is clear. This is the main point here. Is this clear? Tell me, Viramani, Thara,
Yes,
Yes,
sir.
sir.
Yes, sir.
this
Yes,
point is
sir.
clear now. How we have
Yes,
Yes,
taken.
sir.
sir.
This is independent on you. Okay. Now,
Yes, sir.
yeah, switch off your mics. Voltage between slip rings of the circuit you can write, because this is the line voltage. Phase voltage would be equal to, see, line voltage is root 3 times your phase voltage. So this is root 3 times E1 divided by your T1 into 43. So this is voltage between slip rings on open circuit would be this value. So this value happens to be 350. So I have calculated this as your, see, this is the voltage, this is the what you say is that your rotor voltage. So rotor voltage would be, depends upon what, depends upon your stator voltage and the number of turns, that is your 54, and this is your line voltage, root 3 into 44 divided by root 3 into your this 43. What is this 43? From where this 43 came? Hmm? This something I missed here. Na? This is my T1, T2. E2 is equal to root 3. See here. See here where I have started it. Yeah, in the very beginning. Yeah. So you can see now your TR is equal to TS KWS KWR into ER by ES. So if you have to express in terms of your this thing, what I say is in terms of your TR, so you write like this. If you have to establish in terms of ER, so ER you will take here, TR will go down and ES will remain. So this is that, this from this formula we are getting this thing over there. Yeah, one second, one second. Hmm. One second. So yes, here also you have seen this T2 is equal to E2 by E1 into T1. So now your E2 you need, E2 would be equal to E1 into T2 divided by T1. So T1 you have calculated, T2 you have calculated. T1 is 54, okay, and T2 is 43. Okay, this T2 is 43. So 43 and that T1 is 54. Remember that. So now here same thing we are doing it. That is your this thing, your the rotor side voltage would be root 3 E1 into T1 into T2 from that voltage. So this T2 is 43, this T1 is 54. So this is root 3 into E1 is 44 by root 3 divided by 54 into 43. So this happens to be 350 volts. Earlier also we calculated na 350, from where we got. 350 volts. Somewhere it's mentioned also. See here, it's also mentioned it should not exceed 350 volts. So we are seeing that our calculation also, that number of turns. See, earlier we just directly substituted this value. This time we did not substitute this value. This time we have just put the number of turns and everything into equation to cross verify whether our answer is coming correct or not. See, we are just putting the number of turns into play and this thing, and we are automatically getting this 350 because our design is made for this 350 volts. Now you have to calculate your rotor current. Your rotor current would be your rotor mmf in by T2 rotor mmf. Okay. Mm. Now to calculate this rotor current, you have a rating, power rating of a motor divided by efficiency. The power rating of a motor is given as 3 times E stator, I stator, and cos phi. So this power rating 3 times E1 I1 cos phi is equal to your rating of the motor, that is 80 kilowatt. 80 into 10 power 3 divided by your efficiency. Efficiency is like this. Okay, now you want this value I1. So from this very formula, your I1 would be equal to 80 into 10 power 3. 80 into 10 power 3 divided by your efficiency. Divided by your efficiency, you have your E1. E1 is your 440 by root 3. You have your 3 for 3 phase. You have your cos phi is zero point 0.8. You have your efficiency value is 0.85. So you get the value of I1 is equal to 80,000 divided by 0.85 into 3 into 440 divided by root 3 into zero point 0.8. So you get this value around 154.38 amperes. So you have stator current per phase. That stator current per phase now is equal to how much? 0.85 times the stator mmf. So your rotor mmf would be 0.85 times is into ts. This is your stator current into the stator number of turns is equal to ir. This is the rotor current into tr. So you have your ir is equal to 0.85. This current you calculated, this is the stator current, because this I1 was stator. See, remember one thing, when I'm taking I1, that means it is going inside the supply side. So this would be stator. I2 would be rotor. T1 would be stator. T2 would be rotor. T1 means the number of turns per phase of stator. T2 means number of turns per phase of rotor. You can take any which ways. You can take like IR and IS also, or you can take I1 and I2 also. That this nomenclature is up to you. For that, no marks will be cut. But only thing is that the correct format you have to. Now from here, if you calculate IR, you get the value of IR as 0.85. IS you have calculated 154.38. TS, you know, it is stated turns 54. TR is 43. So you get the value of current to be 164.79 amperes. So hence the rotor current per phase, you got rotor current per phase is 164.79. Your stator, this SR is equal to 48. You see this SR 48 you can take any which ways, but it should not exceed 65. And it should, the integral multiple SS minus SR should not be that 0 plus minus P plus minus 2P. That values, apart from that, you can take any value, and which is the nearest harmonics, you can take that also. And this is one criteria. And your T2 you calculated, this is the rotor turns per phase 43. Your conductor slots, you can that ZR. See, ZR would be equal to 6 times T2. See, 43 into 6 you will get around 258. 6 3s are 18. 1 carry, 6 for the 24, so 25, 258. See, ZR you can calculate 258. I rotor you calculated 164.79. E2 you have calculated 350 volts. Coil span is equal to 6. So this was our problem. We have arrived at it. So any doubts you are having in any particular portion, Viramani?
No, sir. No,
Huh?
sir.
No, sir.
No, somewhere. So you are confirm, huh? So let me revise a little bit and let me ask some questions. Hmm? Now you tell me one thing. See, minimum, whenever I'm calculating this minimum area, okay, what I'm equating, flux density or area? Hmm? Tell me, anyone, Unnati, you tell. When I'm calculating the minimum area, what I'm equating? Hmm? Flux density or area? 35 people are present right now. So, Yogesh, you tell me. Hmm? Yogesh? Okay, Bindushri, you tell me. Bindushri? Okay, Radhika? Yeah, Bindushri, you tell me. Are you there, Bindushri? I'll mark you absent. Bindushri is not present. Radhika?
Sir?
No, no, I'm asking to Radhika. Yeah, Shilpa, are
Yes,
you
sir.
there?
Tell me, sir.
Okay, you are there. So now tell me, when you are calculating the rotor flux minimum area, so what you are taking into consideration? Either you are taking into consideration flux density or area. Hmm?
Area.
Huh? Area. Okay. Yeah, you can. Chalo, theek hai. So another thing is that Yogesh,
Yes, sir.
so you tell me what is the difference between a squirrel cage rotor and a slip ring rotor? What is the difference between squirrel cage rotor and slip ring rotor? Hmm? Anything? Anybody can tell? Viramani, you can tell? Dif- Mushtaq?
Yes, sir.
Mushtaq? You can
Yes,
tell
sir.
me difference between squirrel cage rotor and slip ring rotor?
Sir.
See, in squirrel cage rotor, we cannot insert external resistance. Whereas in slip ring rotor, we can insert external resistance. So that's why it is
Yes.
called a slip ring rotor. By inserting external resistance, we can control voltage, we can control torque. Okay.
Yes, sir.
Okay.
Okay, sir. Yes, sir.
Okay, one more thing. Amish Kumar. Avish Kumar. Okay, Avish Kumar. Avi, Abhishek Kumar. Kushwa. Abhishek Kumar. Hi, nahi. I'm marking you absent, Abhishek Kumar. Simply uh, Fakrish Naik. Fakrish and Naik.
Yes, sir. Yes, sir.
Yeah,
Present,
you tell
sir.
me one thing. Today's class you understood. Open your mic,
Yes, sir.
Fakrish Naik. Today's class you understood.
Yes, sir.
So what is the maximum? Okay. Now you tell me what is the difference between this you rotor conductors for three phase would be equal to how much in terms of turns per phase? Rotor turns. Fakrish, how much would be equal my ZR would be how much it would be equal my rotor conductors for a three phase system in terms of turns? Like my Z should be equal to 4 T phase, 3 T phase, or 2 T phase for three phase. It should be 2, 3, or 4, or some other value.
40, yes, sir.
4 T phase. Huh? How you are telling 4 T phase for three phase system? Listen
Sir,
carefully.
6,
When 60 phase. Yes, you out
60
of the
years, sir.
yes. 6 it should be equal to Gagana. Gagana. Yeah, you stop your mic. Gagana.
Yeah, sir.
Yeah. How much should be my Z equal to in terms of T phase? Hmm? It should be
60.
equal to 3 T phase or 4 T phase. Hmm? Listen properly. You are not listening. I know that. I'm seeing you. Yeah, it should be equal to 60 phase. Harishar,
Sir, 40 phase, sir.
how, uh,
6,
40 phase.
3 phase 3 into 2 times T.
2 times T. Because why 2 times T? One conductor is equal to 2 turns. Listen, Gagana. For one phase system, your conductor per phase should be equal to twice the number of turns. This, Okay, twice the number of turns is equal to one conductor is formed by two turns for single phase, and for six phase it is 2 into 3, six phase. Okay, G1M, G1M, G1M.
Yes, sir. Yes, sir.
Yeah, you tell me your relationship between your stator voltage and rotor voltage in terms of turns per phase. Suppose ES should be equal to how much? Or ES by ER should be equal to TR by TS or TS by TR. Okay, tell me.
TR by TS, sir.
ES by ER. T
TR by
stator.
T. TR by TS.
How you are telling reverse? It should be equal to you only see. You are writing down.
Yes, yes, sir.
Hmm. Okay. You switch off the mic. You see that? Okay, switch off the mic. Okay. So I'll be concluding my class here. So these many number of people are present, but I'm not giving attendance to Amish Kumar. Avish Kumar, are you there? No, he's not there.
Abhishek, sir. Abhishek.
Abhishek Kumar, are you there? Is it there? Abhishek Kumar, not there. So this is it. So I'm just conclude. 33 people are there. So why today's such less attendance? Huh? Okay. Okay. Thank you very much. So, but don't talk because the class
Thank you,
is still
sir.
recording. Okay. So take care. Okay.
Thank you, sir. ಏನೋ ಕಾಟ್ಲೆ ಸರ್ದು
ಅವನೇನಲ್ಲ ಹುಚ್ಚಿಂತಾಗ ಆಡ್ತಾನಲ್ಲ
ಏನ್ ಹೋಗಿ ಏನ್ ಮಾಡಿದ್ಯಾ
ಅದೇಗ ಗೊತ್ತಿಲ್ಲ
ಏನ್ ನಿಮ್ ಹೆಸರು ತಗೋತಾನೆ
ಇಲ್ಲ ಇಲ್ಲ ಫೋನೇ ಮಾಡಿ ಹಾ